Hello, my name is Anyi. I'm a third year mechanical engineering student at the University of Birmingham. In this presentation, I'll be talking about my final year project, which was concerned with dropwise condensation on liquid repellent surface patterns. Condensation is a phenomenon ubiquitous in both nature and in industry. We observe it while conducting household activities such as cooking and bathing. Optimizing heat transfer during the phase change process from water vapor to liquid water enables the conservation of natural and financial resources in power generation. There are two main modes of condensation referred to as dropwise and filmwise condensation. During filmwise condensation, a layer of condensate is spread over a given substrate. This prevents subsequent vapor from efficiently transferring heat to the surface of the material beneath. During dropwise condensation, the condensate takes the form of spherical beads. Eventually, neighboring beads coalesce and move downwards, gathering the static beads in its journey. This leaves a large surface area open for further condensation and heat transfer. For this reason, the heat transfer coefficient for dropwise condensation is roughly 10 times larger than that for filmwise condensation. In order for dropwise condensation to occur, the surface must have a low degree of wettability. This is characterized by a high contact angle in the range of 90 to 180 degrees at the interface between the solid surface and the forming liquid. Hydrophobic surfaces have been fabricated by applying a low surface energy coating. High polar molecules such as water have a low affinity to these surfaces and are unable to form strong bonds to the structure. However, these coatings degrade with time, causing the liquid repellent ability of the surface to diminish. Microstructured patterned surfaces have been proven to provide a robust solution regardless of their material energy. They are fabricated with increased roughness and utilize their geometry by trapping air below the suspended droplet, preventing it from penetrating the structure. This state is referred to as the Cassie-Baxter wetting state. Certain structured surfaces can display hydrophobic properties even when the droplet makes contact with the surface. This state is referred to as the Wenzel wetting state. The microstructured surface patterns investigated during the study were fabricated using femtosecond laser processing. During this process, a laser was said to have a pulse rate of 500 kHz and used to machine different surface patterns onto a stainless steel substrate. The topographies on the stainless steel were then reproduced on thermoplastic sheets. This was done by placing the textured steel together with a thermoplastic sheet and applying a hot temperature and load. Studies have shown that condensation-induced failure can greatly compromise the performance of a hydrophobic surface. When vapor is condensed onto the surface, the condensate nucleates at the base of the pillars. As condensation proceeds, the condensate grows in size and merges with any static droplet supported by the structure. This results in a decreased contact angle and repellency of the surface. It is necessary to investigate the mitigation of condensation-induced failure as it prevents the hydrophobic surface. The first project aim was to study the characteristic properties of microstructured surfaces. Aim number 2 was to investigate the failure of these surfaces during condensation. The last aim was to study the dynamic motion of condensate along with the preferred mode of condensation on a hydrophobic surface. These aims were achieved through the corresponding objectives listed in the slide. The first experiment was concerned with investigating the characteristics of structurally hydrophobic surfaces. This study is valuable because it validates the properties that allow a surface to display exceptional repellency against water. This is a requirement for dropwise condensation to occur. The study utilized a gynometer to measure the contact angle formed between a water droplet and 5 different surfaces. 3 of the 5 surfaces were structurally fabricated, while 2 were not. For each surface, the experiment was repeated 3 times and an average was calculated to increase the accuracy of the results. The captured images reveal that the 3 structurally fabricated surfaces produce a water droplet that is more spherical in shape than the 2 non-fabricated surfaces. This result serves as validation for the superior repellent properties of modified surfaces. Surfaces A and B are both made from a polypropylene base material. However, surface B recorded an 8-degree higher contact angle than surface A. This result confirms that there's an increase in surface repellency with increasing aspect ratio. Although in experiment 2, a Peltier module was used as a thermoelectric cooler in order to investigate the failure of hydrophobic surfaces during condensation. The module was attached to an aluminum heatsink in order to eliminate any buildup of heat. The system was powered by a dual-output direct current bench supply. Each tested surface was placed on the cooler and recorded for a duration of 3 minutes. The experiment was then repeated for each surface, but this time, as condensation commenced, the contact angle on the surfaces began to decrease, revealing a gradual loss of water repellency. This serves as confirmation that condensation can inhibit the functionality of microstructured hydrophobic surfaces. The results show that infusing a lubricant into the surface structure results in a decreased initial contact angle. This does not conform with the findings of similar studies. This occurred because a thick silicone grease lubricant was used, which was likely to build up on. The third and final experiment was concerned with investigating the droplet dynamics and mode of condensation on a hydrophobic surface. An acrylic chamber was successfully designed and built for the conduction of this experiment. Its primary purpose was to confine water vapor in close proximity to the hydrophobic surface, thus accelerating the formation of condensate. The front and right chamber profiles were left open in order to observe the formation of condensate, coalescence, and possible droplet ejection. The conical flask was used as a vessel for boiling water, which generated the water vapor required for condensation. Dropwise condensation was displayed as the dominant mode of condensation on the hydrophobic surface. The entire process of this phenomenon was captured during the experiment. Highlighted by the yellow marker, a bead of water can be seen to coalesce with neighboring beads, causing it to grow in both size and weight. This process would continue until the droplet would eventually advance downwards, combining with all the static droplets in its trail. This left behind an exposed area where the cycle can once again be repeated. During the conduction of experiments in this project, several problems were encountered, which may have affected the reliability of the produced results. The camera attached to the gynometer only allowed for short recordings of the surfaces. A larger range of surfaces should have been tested for a longer period of time. Despite these issues, the results produced agree with the findings of accredited sources. It can therefore be concluded that patterned surfaces are an effective solution to water shedding applications. When combined with a low-energy coating and an infused lubricant, a microstructured surface can successfully induce dropwise condensation in a robust and efficient manner. Thank you for listening.